Okay, so in Science 10, you only had work energy theorem problems that involved change in potential or a change in kinetic. In Physics 20, you could have a work energy theorem problem where both change. It doesn't really make it any harder. There's just a few more things to keep track of. Okay, the principle is still exactly the same. So in Science 10, you might have got a question that said, what's the force required to accelerate something from this speed to this speed over this distance? That would have only been a change in kinetic energy. Or how much energy is required to lift something from this height to this height? That would have been a change just in potential. In this course, you could get something like an object is accelerated up a ramp. Well, now both potential and kinetic energy are changing, and you would have to do that kind of thing. It's really not a lot different. It's just that both can change. Okay? So, in understanding what work is, we have to know what the definition of work is. What is the definition of work? It is a change in energy. Specifically, mechanical energy. Okay? So work is any change in mechanical energy. Whenever we use delta, we are subtracting two things. What are they?
Final and initial.
Final and initial. Right? Anytime you have delta, it's something final minus something initial. Now it's going to be energy final minus energy initial. Okay? It's our change in mechanical energy. In Science 10, you learned this, and you also learned this. That you can calculate work by multiplying force times distance. That's still true. Okay? We do add one little thing into it for Physics 20, and that is that we bring in forces that might be at an angle where only one component actually does work. So like the question where I'm pulling the desk, okay, at an angle, I'm only changing its energy horizontally. I'm not moving it vertically, I'm only moving it horizontally. So you bring in a little bit of vector stuff, but it's so rare that you just kind of need to know it exists, and that's about it. Okay? Now, according to this formula here, the relationship between force and work would be what kind? Or let me put it a different way. If I doubled the amount of force I use, how much more work will I do?
Double.
Double. What kind of relationship is that?
Directly
Linear or direct, yeah. Okay? So they have that relationship. If I use twice as much force, I will do twice as much work, provided it's the same distance. The same is true for distance. If I use the same force over 100 meters as I do over 200 meters, I do twice as much work when I go 200 meters. Okay? Everyone okay with that? It's a pretty simple relationship, right? Okay, so that's the relationship between force and work. That's what work is, and depending on the situation, work and energy can be equal, because if you start out with no energy and then do work, the amount of energy you gain is equal to the work you do. Okay, so they can be equal from time to time. Okay, in this situation, pushing the car, if I push that car straight horizontally, and it moves straight horizontally, what will I see if I'm doing work? Or what will happen if I'm doing work? Don't say I'm doing work, because I already said that. What will the car do? It'll move? Okay, in what way? Forward? What kind of movement? Yeah, it should accelerate. If I'm doing work on the car, I have to change the energy of the car. Since it's horizontal, I know I'm not changing its potential energy, because that involves gravity and it's vertical. The car's not moving vertically. Okay? So if I'm doing work on the car and it's moving horizontally, then it has to accelerate, because kinetic energy is dependent on your speed. Okay? So for that to change, I would have to change its speed, which means the car would have to accelerate as a result of me pushing it. Everybody okay with that idea? What if the car's speed doesn't change? Does that mean I'm not doing work? It means I'm not doing work on the car. But I could still be doing work against, well, it wouldn't be gravity because I'm horizontal. I can only do work against gravity if I move up or down. What force might I be working against horizontally? Friction, yeah. Okay, there would certainly be rolling friction, or worse, if the brakes were on, sliding friction. okay? That would be interesting, unless it was like really icy or something. But yeah, if the car was moving at a constant velocity, I'm still doing work. It's just not changing the mechanical energy of the car, okay? In fact, if this is on a frictionless surface and the car is moving at a constant velocity, do I even need to push it? It should move on its own then, right? If there's no friction, Newton's first law should apply, and that thing should keep moving at a constant velocity, the thing can just walk behind and look cool. Well, I wouldn't be able to walk, because there'd be no friction, and I'd fall down. Okay? Is that making sense? Okay, so in order for work to be done, a force has to be exerted through a distance, and that has to result in a change in mechanical energy, either potential, or kinetic, or both. Okay, if I pushed it uphill, okay, then I would be changing both. All right, so we bring in this F cosine theta thing into our formula. That was not in there before, this cosine theta part. It was just F times D, right? The reason we bring that cosine theta part in is because sometimes you exert a force that is not vectored in the same direction as the work is being done, right? Like dragging the desk, or maybe pushing on a car, you push it slightly downwards and forwards. You only want the horizontal component because that's the only part of that force that's actually doing work, okay? Everyone okay with that idea? So that's where that cosine theta part comes in. It doesn't really make it any more difficult, it just takes into account that forces can be vectored. Okay, other thing, work is a scalar quantity. Right, so when I do work, there's no like 200 joules north, okay, or 500 joules down. Work does not have a direction. You change something's energy, you give it the ability to do work. Okay? If I gain energy, I can do more work. Okay? That's what work is. It's the ability or the change in energy, and energy is the ability to do work. Okay, they're kind of like a chicken and the egg kind of thing. Okay. Which is the stupidest thing ever. I don't know why I keep saying it. What came first, chicken or the egg? Egg. Chickens are birds. Birds evolved from reptiles. Reptiles lay eggs. Eggs were around long before birds. Scientific reasoning. Okay? But it's totally true. Anyway, okay, so you can't do work if you don't have energy, because work is a transfer of energy. I can't transfer what I don't have. Okay, so you know when it snows and your parents are like, go out and shovel the driveway, I can't, I got no energy for that. You're lying. But if you actually had no energy, you would also be completely incapable of shoveling the driveway, because that's work, and you have to have energy to do work, because work is a transfer of energy. You move the snow, you give it energy to work. Okay, everyone all right with that? Okay, so work is a scalar quantity. So is energy. But work can be positive or negative. Is that contradictory? Work's a scalar quantity, but work can be positive or negative. Contradictory? Seems like it, right? Seems like positive and negative are vectors, okay? But in this case, they're not.
That's like saying time is backwards.
No, not really. Here's why. Let me explain it this way. If I do work in lifting something, so let's say I take like my coffee cup here, okay, and it's on the seat. I take it and I move it to here. Did it gain energy? Yeah, because now it's higher off the ground. Where did it get that from?
You.
Me. Okay, so I now have less energy because I did work on the cup. From my point of view, that work is negative because I lost it, or I transferred it, or I gave it away. From the cup's point of view, that work is positive. It gained that much. So the positive and negative is your point of view. Did you do the work? If you did, it's negative for you because you transfer the energy away and you now have less. If you're the object being worked on, from your point of view, the energy is positive because you will now have more. Work is a change in energy. If your energy change results in more energy, that's positive. If your energy change results in less energy, that's negative work. Okay? All right with that idea? So energy lost is negative work. Energy gained is positive work. Right? It doesn't involve direction. We're not saying north is positive and south is negative. We're saying positive means you got more, work was done on you. Okay? Negative means you now have less, you did work on something else. All right. Okay, these 4 girls, they're pushing really hard on that rock. But that rock has been there for thousands of years, and it's not going anywhere because of anything they do. Are they doing work?
No.
Nope. Okay, not on the rock.
What are they using energy?
Yes. Why?
Because they're pushing horizontally, and friction's also a horizontal force, so
But friction only matters if I move the rock.
It's because they're gravity.
Aren't they still exerting
The force
force?
is-
They're exerting a force on the rock. What is the rock doing?
Wait, is the rock
Exerting
gaining
back.
energy?
It's exerting a force back. The rock's energy isn't changing, okay? But work is being done on them. That's why they would get tired, okay? They have to resist the Newton's third law of force, okay? That action-reaction force back on them by bracing themselves. When you exert a force, do your muscles get shorter? Right? If you do anything, you lift, push, okay, whatever, your muscles contract. They get shorter. That's a distance. It's measurable. Okay? That's the distance over which the force is being exerted. And that's the distance over which the work is being done. And you have to resist that. Therefore, you expend energy. It doesn't mean you're necessarily doing work, but you are changing your energy. It's being converted into heat, sound. All those things are going into the surroundings. From your point of view, it's negative work. You've lost that energy. You just haven't done it on the rock. Okay? You've sort of done work on the surroundings. You've lost energy to the surroundings as a result of pushing on the rock. Because from a physics standpoint, if I don't do work on the rock, I shouldn't get tired. Well, yeah, but there's the surroundings as well. And exertion is going to result in me losing energy that way. Okay. All right, now vectored forces. This is where this F cos of theta thing comes in. So pretty common thing if I've got the suitcase with the wheels on it, okay, and I'm walking through the airport pulling it, okay, which way am I pulling it? Like this, right? I'm pulling it at an angle. Is the suitcase going that way? Okay, the suitcase is moving horizontally. So this force is not doing work. Neither is this part of it. Why not?
The box is not moving up.
Right. The suitcase is not moving vertically. The suitcase is moving this way, which means that component of the force is what's doing the work, and that is the adjacent side. Therefore, that's how I would calculate the force that is doing the work. Okay? The force I exert is not doing the work. The horizontal component of that force is doing the work.
Why is it only cos?
Well, it could be sine, but most of the time this is the way it goes. Most of the time the angled force is going to result in it's this side. If it's vertical, it's against gravity. We don't bother calculating it because we know we can just go m times g to get the force against gravity. Okay? Does that make any sense so far? Okay, so that's why we put that cos of theta part in there, okay, is just to get the part of the force that's actually doing work. So the big thing here is not so much that you learn to use that formula, but that you recognize you can have a force, but not all of it does work. Okay? Only the part of it that results in motion or is parallel to the motion is going to actually do work. Okay? So we could have an example like this one. Let's say that force is 45 newtons. Okay? So this force here is the 45 newtons. Okay? This angle here is 30 degrees. Okay? And I pull the suitcase for 75 meters. Okay? So if I do that and I want to calculate how much work is done, okay, I use that formula, F cos of theta times D. Okay? So 45 newtons is my force times the cos, sorry, that's 50 degrees, not 30. 50 degrees times 75 meters. And I get 2,170 joules. Is that a lot of energy? Actually, it is. That is actually a fair amount of energy. this obviously is not a very good set of wheels, okay? Because that's a lot of energy for pulling something 75 meters. Okay, now, how will I recognize or identify that work has been done over that 75 meters? Okay, it's moving, but it could move and I still haven't done any work on the cart. What are some other signs that I'm doing work? If I get tired, okay, I'm expending energy.
The net force is lower than the applied force?
That might be true, but it's not going to be evidence that I've done work. How will I know work is getting done?
You're moving.
Oh, we already got that, but how?
The transfer of energy.
What will the movement look like? Constant velocity or accelerating?
Accelerate.
Okay, that's what I'm looking for, right? If I'm going to do work, I have to change the kinetic energy of the suitcase or luggage carrier, whatever it is. Okay? If I pull it at a constant velocity, I don't change its kinetic energy. It has to accelerate for me to change its kinetic energy and do work. Now, if I make this thing accelerate for 75 meters, I'm probably sprinting by the time I'm done this. That's probably not realistic. Okay? I'm more than likely pulling this at a constant velocity. If that's the case, where am I going to see evidence of work being done? Because I'm still doing work, just not on the cart now.
The initial velocity, final, increasing.
But that'd still be accelerating. So now I'm saying those two are equal. Initial and final are equal. Okay.
Energy use.
I'm going to use energy. What am I using it against? What is it doing? What force am I working against in pulling this thing horizontally?
Friction.
Okay, what does work against friction look like? Feel like, sound like? Heat, sound, squeaking, okay? Feel like, hot, right? If those are wheels, they've got bearings in them, yes? Okay, to turn so that they can turn easily, right? Are those bearings going to get hot?
Yes.
Yes, because my mechanical energy is working against friction. And when I do work against friction, friction turns mechanical energy into heat and light and sound. Okay? Those are the evidence of work being done against friction. Okay? Evidence of work being done on the cart is the cart goes faster. VI and VF are different. Okay? That's the other evidence. So there's two ways to tell whether I'm doing work. And actually, in the real world, both would happen. Okay? The cart would accelerate and it would make noise and it would get warm and all of that stuff. Okay? Everyone all right with that? Being able to recognize work being done is an important part of work energy theorem. Okay? In the strictest sense, work being done means something goes faster or something goes higher. Okay? Change in kinetic, change in potential. Right? Wasted energies are the frictional ones. Okay? Heat, sound, light. All right, in this situation, doing bench press. Got a 710 Newton barbell. About like 165 pounds. It's a considerable barbell. Okay? And I want to push it up. But I just want to push it at a constant velocity. Am I still doing work?
Yeah.
Yeah. What am I changing?
Potential.
It's potential energy. Okay. In order to make this thing move upwards at a constant velocity, okay, knowing that its weight is 710 newtons, how much force do I have to exert? 710 newtons.
It doesn't balance outcomes that make it go up.
It moves at a constant velocity, which is also true when the net force is 0, right? Okay, so I push upwards with 710 newtons worth of force for 0.65 meters. Can I calculate how much work I do?
Yes.
Yep. Okay, now, I could do it with that very simply because the force and the distance are parallel, right? They're in the same direction. If that's the case, what's theta? What's the angle between my distance and my force if they're parallel? 0. What's the cos of 0?
0.
Nope.
1.
1. Okay? If it was 0, I wouldn't be doing any work, would I? Because I'd have force times 0 times d. Well, that 0's in there, everything is moved. Okay? The cos of 0 is 1. So when forces are parallel, I don't bother putting in cos of theta. Okay? Because I know the cos of 0 is 1. That's why we can just do force times distance when they're parallel. Okay? So when I push this thing up, what I'm really doing is 710 newtons times the cos of 0 times 0.65 meters. Okay? When I do that, I think I get 462 joules. Okay? So I have changed the mechanical energy, all of it potential, of the barbell by 462 joules. Everyone all right with that? Okay. What happens if I lower it?
Double the distance.
Well, but they're in different directions.
Oh, do they even out? Since you've gone that.
Sort of even out. We're on the right track here. Okay, I gave that barbell energy. When I lower it, what happens to that energy?
Oh, it's good for him.
Well, are you dropping it on yourself or slowly
Yeah.
lower?
Okay, there's a good point. What am I doing? Am I dropping it on myself? If I'm dropping it on myself, it's going to do work on me, isn't it? Yeah? It's got 462 joules of energy. If I drop that barbell, it's going to change my shape in an undesirable way, and that counts as work.
But isn't
Okay.
it no energy if you just drop it? You're not using any energy.
Then I wouldn't be using any energy, you're right? It would just be converted into, well, changing the shape of my rib cage probably, okay? So that's not good. When I lower it, because if you're working out the right way, and I see people do it the wrong way all the time, okay, my up and down look the same. Okay? I don't do the up any faster or slower than the down. Everyone I watch, especially high school kids, no offense to you guys, okay, when they do the workouts, they're like, yeah, I got it up, yeah, and then they just like drop it back down to their chest, okay, or put it on the rack or whatever. It's like, it's half the workout. The other half of the workout is doing the exact same thing when lowering it. Well, if I lower it at a constant velocity, how much force am I using? Same. Yeah, still 710 newtons. Is my force still up when I lower it? It is. So this free body diagram looks exactly the same when I lower it, except for one thing. What's this angle? 180. What's the cos of 180?
1.
Nope.
2.
Good job.
Nope.
Negative.
-1. Does that make it work?
Yeah.
It does, because now it's representing the work done by the barbell, or the energy lost by the barbell. I have to do work to prevent it from crushing me. Okay? That means the barbell transfers work back to me. Okay? I'm going to convert that into sound, a lot of grunting, okay, and heat and whatever, okay, but it's going to get turned back into other forms of energy. The barbell loses that energy. Okay? So from the barbell's point of view, when I lifted it, the work was positive. From the barbell's point of view, when I lower it, the work is negative. Doesn't matter where it goes, it's lost by the barbell. Okay? This is all from the barbell's point of view. Okay? So that's where that cos of theta part can come in. Because remember, it's force times distance. Distance is scalar. It doesn't care which way it is. Okay? It's the cos of theta part that makes the work negative. Okay? Now, we could also just say force times distance and go, I recognize that this is energy lost by the barbell, so it has to be negative. I'm fine with that too. It can be intuitive like that. Okay? All right. Understand the difference between positive work and negative work?
Yeah.
Okay? Positive gain, negative loss. Okay, so a couple of things. First off, units. We haven't even talked about the units for work. Okay, units for work are joules, yes?
Yes.
What's a joule? Yeah, that's usually the answer I get. I don't know.
Work.
Work is measured in joules. Okay, what do I multiply together to get work?
Newtons
Force.
and And
Force and distance, okay, so
Newtons per meter.
Newton meters, not newtons per meter, that would be force divided by distance. All right, what are the units for newtons?
Kilograms per second.
Kilograms. Okay, here's mass times acceleration. What are the units for acceleration?
Meters per second
Okay,
squared.
kilogram meters per second squared are the units for newtons. I multiply that by meters. What are the units for a joule?
Kilograms meter squared second squared.
Yep, kilogram meters squared per second squared. Okay, you can write J, we can say joules, but we have to recognize what the fundamental units of that are. Okay, because if we start doing work energy theorem calculations, we have to recognize if I divide by force, that I'm taking the kilogram meters per second squared out of there, and I'm going to be left with meters. Okay, things like that. So it's important to understand what those units are. You don't necessarily have to write them. J is fine, okay, but know what the J stands for. Joules, I mean kilogram meters squared per second squared. Okay, and just important to know the fundamental parts of that. Okay, so the work energy theorem says that work is a change or a transfer of energy. Okay, which means you have to have energy to do work. Okay, you cannot transfer what you don't have. This is not a credit card. Okay, you cannot spend what you don't have. So you have to have energy to do work. Okay, and similarly, once you have energy, you have the ability to do work. Okay, so they go together like that. Work is a change in energy, and energy is the ability to do work. Now, the two types of energy that are part of mechanical energy are kinetic energy, okay, and potential energy. Now, looking at this formula here, if we go back to the barbell, okay, when we calculated the work done, we did this, force times distance. And we said that the weight of the barbell was 710 newtons. What force is weight? Force of gravity. Okay, how do I calculate the force of gravity?
Weight times
Not weight times 9.81.
mass.
Mass. Okay. Okay, so these two forces are the same, right? When I push the barbell up, I use the same amount of force as its weight. What do we call a vertical distance? Well, it could be down.
Normal.
Starts with H. What's a vertical distance? Height.
Vertical.
M times G times
Height.
those two formulas the same? Yeah. Okay, force times distance is change in energy. If I lift something, it's force of gravity times the height I lift it. Okay, those two formulas come from the same place. Okay, so something's potential energy then depends on its mass, the acceleration due to gravity, which is not going to change in the middle of a question, it's going to be 9.81 most of the time, okay, and the height you lift it, or lower it, okay, as the case may be. All right, everyone okay with that? And all these relationships are all linear, right? If I have to lift twice as much mass, I'm going to have to do twice as much work. If I'm going to lift a mass twice as high, I'm going to have to do twice as much work. If I go to a planet where G is twice as much, I'm going to do twice as much work. Okay, everyone all right with that? Kinetic energy. What's kinetic energy dependent on? Mass and
Velocity.
actually speed, scalar. Yeah.
Oh, right, yeah.
Yeah.
That's what it's got.
Which one has a bigger effect on kinetic energy, mass or speed?
Speed.
Why?
Because it's squared.
Because it's squared. Okay. If I have my truck empty and I'm driving to fill it up with something, okay, it has a certain amount of mass. To stop it requires a certain amount of work. If I go and fill the box up with dirt, so much so that now my truck has twice as much mass, is it going to take twice as much work to stop it? Yes, that's linear. Okay. If I double the mass, I'll have twice as much energy. Okay, but if I double the speed, I have how much more energy? Four times. Okay, it's an exponential relationship, right? Speed has an exponential relationship with energy, which means when we start talking about work energy theorem, okay, that that relationship, that exponential relationship, applies to the amount of work required to stop something. Okay, so if I have a vehicle traveling along the road, okay, and I want it to stop, its final energy would be 0, okay, and the work needed to stop it would be equal to its kinetic energy. Would you agree? Right? Like I want to go from having X amount of joules of kinetic energy to having 0 joules of kinetic energy. That change in energy is the work that's going to have to be done to stop that object. Okay? Now what stops your car?
Brakes.
Brakes, yeah, not something else. Okay? So you apply your brakes, okay, and how do they stop you?
They,
Okay, brake rotors, yeah, you've got the calipers that squeeze the rotor, okay, but that's what's going on. How does that take your kinetic energy and make it 0? It changes it, yeah. It turns it into other forms of energy that are not kinetic. It turns it into heat and sound and light. What's that? Yes, it slows the rate at which your wheels are turning as long as they don't lock.
Okay.
If they lock, then you slide, and that's going to be a lot less effective because now it's relying on the tires and the road converting your energy into heat and sound and burnt rubber.
So it like kind of squeezes the wheel.
Yep. So if you look inside your wheel, you can see a silver circle. That's your brake rotor. Okay? You can also usually see something that's kind of clamped onto it. That's the caliper. Okay? Your brakes work by squeezing that caliper against the rotor, metal on metal. Okay? That's what stops your car. All right? And your anti-lock brake system basically makes sure that that rotor is always spinning with the caliper. Okay? If the caliper squeezes too hard, the wheel stops spinning and you slide. Right? It takes longer for you to stop if you're sliding because that's kinetic friction. Okay? If your wheels can continue to turn, you'll stop more quickly and have the added advantage of being able to steer while slowing down. Okay? That is the major advantage of anti-lock brakes. Okay? Is that if your tires are turning, you can steer. If your tires are sliding, you can turn your wheel like this and you'll just keep going straight. Okay? So the major advantage is not in stopping distance. There's a slight advantage there, but the major advantage is with anti-lock brakes, you can continue to steer the vehicle while stopping. Right? If you've ever had your anti-lock brakes kick in, you'll recognize it by it feels like the pedal is kicking back against your foot. Okay? Because what's happening is the brake cylinder is just actuating faster than you could possibly ever hope to pump the brakes. Okay? And just finding that pressure where the tire will continue to turn, okay, while having the brake applied. Sometimes it fails, okay? And it's so slippery that it just completely lets go, and that's the only way the tire can turn, okay? And then you just keep sliding, okay? Or you just keep turning. Right? Now, let's say I'm looking at a situation like I'm in a playground zone, all right? If I want to stop, I'm going to have the force that my brakes can exert, or the force of friction, okay, multiplied by the distance over which that work will be done, so that's my stopping distance, equal to the amount of kinetic energy I have the moment I apply the brakes. Agreed? Okay, that's the amount of work that my brakes have to do. They have to take away all my kinetic energy. So if we just said that there's an exponential relationship, that means if I go 30 kilometers an hour, I stop in a certain distance. How much farther do I travel if I'm going 60? 4 times. It's an exponential relationship. If I have 4 times as much energy at 60 that I have at 30, I'm going to travel 4 times further. Think about it. This number is the number, okay? If this is twice as big, this number is 4 times as big. That means that these two things have to change as well. If my brakes can only exert X amount of force, I'm going to have to go 4 times further. Okay? And I can prove it to you mathematically. let's say we're driving a 1,800 kilogram vehicle. Okay, we'll say that our brakes are capable of exerting 12,000 newtons worth of force. Okay, and that we are traveling in a playground zone at the speed limit of 30 kilometers per hour, which incidentally is 8.3 meters per second. Okay? Can I calculate how far I would travel if I have those numbers? Yeah. Okay, so all I do is solve for d, right? So I'm going to say that d is 1/2 mv squared over f. So that'll be 1/2 times 1,800, the mass of the car, times 8.3 squared, divided by 12,000 newtons. Okay, now this is 0.3 repeating, so, all right, so let's just get those numbers for us here. So 30 divided by 3.6 gets me the 8.3. Okay, so now I'm going to go 0.5 times 1,800, so times my mass, times my speed squared, divided by my braking force. All right, so that means my car will travel 5.21 meters before I stop, from 30. Okay, that's not too bad. That's a pretty quick stop. Okay, provided I'm paying attention. Okay, not impaired in any way at the wheel. I would probably be able to stop in time to not hit a child, or I would have changed my energy enough that I wouldn't seriously injure them were I to hit them in that 5-meter space. Okay, that's the whole reason we have 30 km/h speed limits in playground and school zones. Now, if this changes from 30 kilometers an hour to 60 kilometers an hour, because someone's an idiot and is going twice the speed limit through a school zone, okay, that's my speed now. Okay, if I plug all this same stuff in with that speed, okay, so I go 0.5 times 1,800 times now 60 kilometers an hour, and then divide that by my braking force, because my brakes are still the same. Okay, so I go from 5.21 to 20.83 meters. Whoop. This number divided by this number. Just do what I want. There we go. Looks like 4 times further to me. Okay, there's an exponential relationship between speed and stopping distance.
Is this if you like stopping where your car like it was like slamming on the brakes?
Yep.
You still travel?
So friction's not a factor?
No, friction is the force we're using here. When I apply my brakes, I'm relying on friction to stop the vehicle. Right? The brakes use friction. Okay?
So the force of friction is 12,000.
Yeah. I mean, think about it, it's a heavy car, right?
Yeah.
If we simplify it to it's not the brakes and the caliper, it's the tires on the road, definitely. Yeah, there would be a big force. It's probably bigger than that. I just picked a random number. And it's probably more than that. You would stop pretty quickly from 30 if you were in a reasonable sized vehicle.
So if you slam on the brakes when you have like 80 kilometers an hour, you still travel 20 meters?
Well, not 80, that's at 60.
Well, 60.
Yeah. No, you would. It's a long way, right? That's why we don't want to speed through a playground zone. Okay? Now, obviously, nobody is dumb enough to do this, to go 60 through a playground zone. Okay? Or I'm shaming you right now. One or the other. Okay? I'm fine with it either way. Okay? So, but do we all justify this? I'm just going to go 40. Because 10's not that much. 10 kilometers an hour, it's 40 and 30, they're close. Doesn't make that big a difference, right? We justify that to ourselves, okay? Because we say 10 kilometers an hour is not a big deal. Well, guys, 40 in meters per second is 11.1. Okay? You do this calculation, same car, and then divide that by your braking force, you go from 5.2 to 9.25. It's almost double. 10 kilometers an hour, and it doubles your stopping distance. Speed has an exponential relationship with energy. And the more of it you have, the further it's going to take you to stop. Okay? So that 40 kilometers an hour, that 10 kilometers an hour you gain, which makes a grand total of like 8 seconds worth of difference through a playground zone, okay, if that, is going to increase your stopping distance by nearly a factor of 2. Okay? That's a long way if a kid runs out. Okay? That's why they enforce those speed limits so strictly. It's also why speed fines double in a construction zone. Okay? People are vulnerable in a construction zone because they have their backs turned, they're busy, they're concentrating on their job, hopefully. Okay? And so they may not see you traveling too fast. Okay? So you have to go the speed limit in those places. Okay? Does that make sense? It's a very practical application of work energy theory. Okay? Now, this is all, of course, assuming that you are paying attention. Okay? If you are impaired or distracted, there's going to be a delay before all of this happens. Okay? That delayed reaction. Okay? That increases how far you're going to go because you're going to continue to travel even if you're at the speed limit at 8.3 meters per second for as long as it takes for you to go, oh crap, there's a kid in front of me. Okay? And I say that because of how rampant texting and driving is. Okay? I know, because when I leave school here, if I'm leaving at the same time you guys do, which quite frankly I avoid doing, I'll stay here and wait until you guys are all gone. Okay? When I look into other vehicles, I gotta tell you, I am dismayed by the number of people who have their phone out while they're operating a motor vehicle. Do you know that statistically, texting and driving is worse than being drunk at the wheel?
What?
It's true. If you are drunk, and I'm not saying that drinking and driving is okay. Please do not misconstrue my message here. Okay? But here's the thing, guys. A drunk who's paying attention reacts late. A person who's texting reacts never. You react when you hear the thump. And it's not funny, but it's true. Okay? Distracted drivers are statistically worse than a drunk at the wheel because they don't react at all. A drunk reacts slow and late. A texting driver reacts never. Okay? And you can see this if you look at like accident scenes. They show like a drunk, there's skid marks. A distracted driver, not until after. Okay? Because they don't ever hit the brakes. They just hit whatever they hit. Okay? Like they dude who took out the light pole out there. Okay? Like I don't know how that happens other than being completely unaware of your surroundings. The road conditions were perfect. Okay? There was no reason to take out the entire signal post there in front of Darcy Crossing. Okay? I still cannot fathom because it couldn't have been a small car either because they snapped it clean off. Okay? So not only were they big, they were obviously going real fast too. Okay? Yeah. Okay? All right. Food for thought.
An ad.
All of you.
What? You know.
Food for thought. Put your phones away while you're driving. Please, I beg you. I have children. Okay?
Don't forget to give your